Okay. Can we start? Okay, hi. It's me again for this week. And today we're going to have the session about pandas. But first of all, I added a mid-semester evaluation, which you find on StudyP here, or just on the normal overview page. So here, that's an evaluation. We would be really grateful if you could fill that out. It's the length of a normal evaluation. We used the template from a normal evaluation and translated it more or less to English. So if you would fill that out, we would be really grateful because it's really useful to have feedback on what we're doing and how we're doing it and so on. It's until next Monday. Yeah, I think it's 1 week until next Monday. Even though next Monday there is no lecture, as you may know. Yeah, by the way, because there's no lecture next Monday, the homework for today, from today, is going to be due in 2 weeks. So in exactly 14 days. Yeah, then I think we kind of have to apologize for the last homework because nothing really worked. Sorry for that. It was really confusing for us too. So who got it? Who got it running? For whom is the homework already working and it's submitted and it passes? Okay. Because I will present the sample solution now because I don't see a reason why not. I know the due date is for this homework, the due date is tomorrow, so the other ones can just have a good look at the sample solution and it may probably help. Okay, so, oh yeah, before I start that, so you know that, so we pushed some changes to, I can't see anything. So we pushed some changes to the repository midway, and by some I mean a lot. And somehow it didn't get to all repositories. So this here is the homework, and this here are the students. So there are, if you have like 20 commits, 15 or more commits, then you got it. And if you don't have that many commits, then you don't have the new changes. Sorry for that. I don't know why the script didn't work for that. I'm trying to fix it, yes.
When was the last update?
The last one was, I mean, you can just look at the, why does this do that? You can just look at the,
how many updates were there? Just one?
Wait a second. So the latest commit should be update weekly to show images again. Or the name would be incorporated the following commit from base : updated weekly to show images again. This here is only the readme. This is nothing breaking, but the other ones are breaking in part. Because it depends which operating system you have. So different operating systems use different fonts. And because the fonts are different, we compare the images pixel-wise. And that sometimes is wrong if you have another operating system. So you can either, if you are one of those who have not many commits, you can either wait for us to fix that, even though I don't know what's wrong with that, or you can simply, if you go on your repository, what you could do, but do it of course with care, you can go on the settings and then delete your entire repository and then accept the assignment anew. And if you do that, and then of course you have to back up your files locally, and then you have to delete your repository on GitHub, you have to delete the files locally, and then you can do that anew. Or you simply copy the respective files from the distributing repository. I don't know why it doesn't work, I'm sorry for that. I hope we get it fixed. Okay. Good, so next up, the sample solution. Okay, let's look at, so this is Atom. It's really nice because I can just, if I have a markdown file, I can just press Control, Shift, and M, and it will show me the markdown of the file, which is pretty nice. Okay, first task was the histogram. Well, the histogram is actually there weren't too many problems, so this here is how it looks for me if I print it. Important was that you see here it goes only until 0.4, even though there are hundreds of values. Why that? Because we want the density. So if you plot a histogram with density equals 2, you will plot, so all of these here will sum up to 1 because we got a probability density function. And if we set bins equals auto, then it will make, so we in our sample solution use bins equals auto. I think it are 27 bins, but looking that manually is probably a lot of work, and bins equals auto is what we wanted to have. And then of course we need access labels for density, and that this here is our random data. Questions? Okay, moving on. Average temperatures. An important thing is that if we don't specify that, if we don't say that you explicitly have to write something, then you probably don't need to write that something. So I've seen many people, for example, trying to align the figure or have set x limits or something. You don't need to set x limits. We said you need to set y limits. Therefore, you obviously have to do that. Besides that, not much else. Okay, so we start by making two subplots where we have obviously two plots above each other. And then we want to plot the month here from 1 to 12. So we made here an array, which is a range, np.range until 12, which is 0 until 11. However, it doesn't matter where you start because you have to override that anyway. So it could go from 0 to 11, it could go from 1 to 12, it could go from 100,000 to 100,011. That doesn't matter because we have to override that anyway. And then, well, we want to go for all the items in the city data and plot them. So we have on the x-axis we have the month obviously, and on the y-axis we have the temperature. So we can just go through that dictionary and plot it. So we have two subplots here, therefore we have two axes, axis 0, which is this one, axis 1, and we simply plot the ones, so the first ones are the low ones and the second ones are the high ones. So we can just plot them like this. And then the name of the city is the label, because if we plot the legend later, we need the name of the city for that. And then the upper one, as we see, doesn't have any x ticks. So this, that we don't have those here, those are x ticks. We don't have them, therefore we simply say, well, x ticks is an empty array. I think we could also say none or something. Well, we have the y label, obviously. And then for the second one, we have to differentiate between x ticks and x tick labels. Because we said, so we said that we plotted it from 0 to 11. So we have points at 0, 1, 2, 3, 4 until 11. And we have to say, therefore our x ticks here have to be the same, because we want to say, well, make a tick for every position of the plot we have. If we wouldn't say the x ticks here, I think the standard from Matplotlib is that it only makes every other tick. So it makes 0, yeah, it makes 2, 3. So this here is rather useless for us. This doesn't make any sense. So we have to set the ticks manually. And then the x ticks labels, well, we plotted from 0 until 11. So this here is the value for 0, this here is the value for 2, and so on. But we want the tick labels because we start counting at 1, not at 0. We have to say that the x ticks labels are the same one, just plus 1. So it's in range from 1 to 13. And then here we also have the y label there. Here we also have the x label. And that's that. And then for both of them we want the legend, and for both of them we want the y limit, because that was written in the exercise. So just to show you, it could actually, so if I said it's a range, so I can also have it from 100 until 111. And if I now plot it, it still looks just the same and it's still correct. Only if I had, for example, another x limit, then I would need Then I would need, if I say I want my x limit to be from -1 to 13, and it's a y, not an x, then of course I wouldn't see anything now because we're plotting from 100 on and we're showing the plot from 0 to 12. That doesn't make much sense. So now I would need to have it at the correct position. Oh yeah, that wasn't even correct. I would have to say until 12. Because the last one is inclusive here. Yes?
Is it x fixed for the position of each tick? So if you put 100 to 112, shouldn't this be shifted somehow?
Yes, but if you don't explicitly set an x limit, it is shifted, but the view of the entire plot, well, the entire plot would, so if you said your x ticks are somewhere else, then your entire plot may be here, but because Matplotlib automatically generates the best view, it would also generate a view here, as long as you don't explicitly say make a view right here. So it just moves along with wherever your ticks are. And your x-ticks labels are just what's written behind each tick. So x-ticks labels, x-ticks, and x-limit are all connected with each other. They're all dependent on each other. Anything else? Okay, then bar plot, where we only have one subplot here. And then we wanted, because this is obviously sorted, we need to sort the dictionary. What we do here is we sort obviously by with a key, and the key is the second number. So it sorts the entire dictionary by its values. Note that this here now is, okay, I don't have it here. This here is, however, a list. It's not a dictionary anymore. Why? Because dictionaries can't be sorted. But data.items makes a 2D list out of a dictionary anyway. Okay, then we have our sorted data, which is now, we can print it. What is that? Like this sorted two-dimensional list. So we have city name and the rainfall, and then we want to split it into city names and rainfall, and for that we simply have the zip operation. So this here makes two lists out of that, namely cities and values. That's where we assign them, and both are still sorted. So we now have a sorted list of cities and a sorted list of corresponding rainfalls. Then we want to calculate the mean, which is simply with NumPy. And then we said we want to have a line at the mean. The command for that is ax.hline. I've seen some people plotting it instead of running ax.hline, and then it looks differently. I didn't even know that, sorry, but the correct command to plot the horizontal line is ax.hline. Okay, and then we make the bar plot, which is simply ax.bar with cities and values. So this will print, well, obviously all those bars. However, it will print them all in the same color. And this is where this, what's the name again? The thing which, if we assign that, oh geez, what was the name of that? Artists. So we create here an artist, yeah, which contains all the bars. And we could simply run ax.bar and then we would lose the reference to the artist, but we can also save the reference to this artist, and then we can iterate through that and change the color in retrospect. Because if we iterate through bars now, we can have bar, which is every single one of those. And if we zip bars and height, we make a new list which contains the reference to each bar and the corresponding height as a two-dimensional list. Okay, and then we can loop through that and check if the height is bigger than the mean, and if it is, we set, if it's not, we set the color tomato, which was this tuple, and if not, we set the color steel blue, which was the number. So we could just as well use the tuple or the number here. NumPy, Matplotlib has a bunch of ways how to print colors, how to set colors. Yeah. So the alternative to this here, to making the artist and then looping over, yes?
One question concerning the color. In the task description, there was this RGB tuple, which
Yeah.
I think it started with 260.
Yeah.
Yeah. But in the lecture script of last week, it said that the values for the RGB tuple have to be between 0 and 1. So you can find out the corresponding color, but somehow the definition.
Oh yeah, you have to divide by 255. Because, why that? Well, that's how well RGB colors on every computer. So every computer has 255 to the power of 3 colors, and many programming languages want them to be between 0 and 1. Haha, between 0 and 1. Another caveat. Yeah, okay, you have to divide by 255. Sorry, we could have said that. Okay.
It was in the lectures next time.
It was. Okay. Another way. So here we make the artist and then we loop over the artist. Another way how to do that. Thanks, Lucas, by the way. Is we could define the colors in advance. So this here basically does the same as the one above in a single line. And we could also define a list of colors in advance, where we have for every bar we simply have the color predefined, and then we can simply make ax.bar with the colors. However, if you do it like this is something we also didn't know before. If you only set the color, there's 1 pixel at the border of each bar which doesn't have the color, which is why you also have to set the edge color if you do it like this. So if you don't make an artist and iterate over this artist, but set the color directly in advance, then you also have to set the edge color. Yeah, in this case it's actually not even necessary that we define bars because it can stay anonymous, it wouldn't matter, because we don't need to re-loop over that. Okay, and then we have to set the Y label with a tech-like string. This is how the tech-like string looks like. We have to set the xtick labels, because so we have to do that explicitly because we have to rotate and horizontally align them. To do this, and then we're done. Oh yeah, we need the legend here for the mean too. Okay, any questions to this? Yeah.
Just regarding the height, you can also just say bar.getHeight, and then you don't need to get the height from the data.
Is the height? Is it exactly the same number? Ah,
Yeah,
okay.
the same number.
Okay. So we don't even need to zip this.
Probably depends on the y-axis what the height is.
Okay, so we wouldn't even need to zip. Thank you. Okay, and the last one was this Inferno kitty, where we have to put the kitty, plot the kitty on the color map. So the biggest problem here was, but I think we explicitly wrote it, right? We did pixel values from 0 to 1. This is the same thing as you just said, Moritz. It's if you don't explicitly say, so the command to print an image is axis.iamShow, but if you don't explicitly say that you want the values to be between 0 and 1, then it will print values between 0 and 255. And then your image looks just like the sample solution, but it's completely different because our values are off by up to 255. So what you have to do here is you have to say vmin and vmax, and if you say vmin, so I think vmin is not even necessary, but if you have the maximum pixel intensity set to 1 instead of 255, automatically divide by 255. Okay, and then we have to turn the axis off because otherwise we would have some border around here. And then we have to pull out the color bar as well. The color bar we have to plot without any arguments. So this is just how we want to do the color bar. This is what I meant. If you don't explicitly write something, you probably don't need to do something. So the color bar, blah, 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 blah. So there are no arguments besides the image here for the color bar. And that's then the Inferno kitty. And that's it. Any more questions to this homework? Yeah.
The last exercise,
The Inferno
kitty
kitty.
one.
Yeah.
What happens if you show the plot before, like in the function, if you show it?
If I would now fit that show.
Yeah. then what happens to the output? Because
Is it removed then?
it is removed, but it didn't pass the test anymore.
But you showed and returned.
Yeah,
Okay.
because then the pixel size of the image that that got returned was bigger or smaller than the picture that you would normally receive.
Okay, I'm not sure right now. I don't think it would.
From
I don't see
the
the reason why.
plot show, I just copy pasted from the lecture, and I accidentally copied the plot show or figure show at the end,
Yeah, it's plt.show, so
Yeah.
that's one.
and then it didn't work. But just if you
Anybody else have that issue?
No, but considering like this like PLT is like this like states machine or whatever, maybe you change its state after
Yeah, I would
you
say, I would
show
think
it.
so too.
yeah.
And just don't plot it. Okay, so that much for the homework. We're gonna start with pandas today. And the next 3 lectures are gonna be about pandas because pandas is really important for you. So what does pandas do? Pandas is a library for fast and efficient computation of big data sets. So the main thing of pandas is that it provides the series object and the data frame object. Series and data frames are basically, so a series is basically like a 1D NumPy array and the data frame is basically like a 2D NumPy array. And that's already it. They just are indexed nicely and they provide more methods, but that's the most important thing. So you have series and methods on that, and you have the data frames and methods on that. And pandas is even more fast and efficient than NumPy because it's built on top of NumPy. And actually, underlyingly, it always uses NumPy. We're going to talk only about that for now. Next week, Rüdiger is going to talk about relational algebra because pandas knows relational algebra, and with that, pandas is basically as powerful as spreadsheet programs and databases, so the SQL-like databases. And then we're going to talk about clean data and what you want to do if you have your data in a special way anyway. Yeah.
We maybe
Where was that, by the way?
think like on the wall there.
Oh, how lame is that?
Yeah, this good enough.
Okay, pandas. It has become, so just like we import NumPy as NP, it's standard to import pandas as PD. And because pandas, why does that now still work? And because pandas underlyingly uses NumPy for many things we do, we have to import NumPy as well. Okay, so a pandas series. We simply make a pandas series by saying pd.series. And then its arguments, so in the constructor we need, for example, a list or a NumPy array or many other things. So now I have a few numbers here and numpy.nan, not a number. So like I said, pandas is used for data sets, so for any kind of data set. And in many kinds of data sets you have missing values, and pandas uses nan for missing values. So pandas automatically makes an nan if it encounters a missing value. It doesn't use that for example, divided by 0, because it's reserved for missing values. Okay, now we see we have the series, we have index, and we have the corresponding value. So this looks basically just like NumPy, right? But the type of that is a pandas series. We can look at its values, and we see that the values, where it's obviously what we said they should be, but we see that the values of the series are actually in fact the NumPy array. So under the hood, pandas uses a NumPy array. However, the difference to NumPy is that pandas explicitly gives the data an index. You can look at the index of the data, which in this case here, because we had simply 0 until 3, simply a range index. But there are many others. So the type is a certain pandas type, and if we make a list out of that, we simply have 0, 1, 2, 3. So we do have the data and an index. And just like with NumPy arrays, we can access the underlying data with our square bracket notation. And we see, well, this is just like in NumPy, right? We take exclusively, we don't take the number 3, but we have 1, and we have number 1 and number 2. So the second and the third element. And if we look at one certain value, so this here is the range, as you know, this here is just one value, and if we look at that value, we see it's a simple NumPy float. But like I said, so we see that there are many operations for pandas series, so we know a few of them already. So we know what what the dunder method add does. We can add two pandas series. So this is apparently defined. We can have a logical AND, we can make an array out of it, and so on and so on. So many of these standard Python methods work on that, but as we see, we have a bunch of other functions, which are not there for normal NumPy arrays. But we can generally see a pandas series as a generalized NumPy array. So it's a NumPy array that basically has this index thing. And generalized because our index in NumPy is obviously 0 until whatever the length of our array is. Whereas in pandas, we can set an explicit index. So when we create a series, first argument is again our series, and then we can have the argument index. And now we don't have 0 until 3 as index, but ABCD because we said so. Okay, we can even change the index afterwards. I can change the attribute data.index, and I can make a new index. And the difference to a normal NumPy array is now that we can't only index by the number, but we can also index, for example, by this explicit index. So we can say data at the position of the index B. And now data at the position of the index B is the same as data at the first position, 0, 1. So this here is the very same thing, the result of both is 0.5. So we can index it by the explicit index and by the implicit index, which is basically the same one as NumPy had. Yes?
Why would you use that?
Because sometimes you need the one, sometimes you need the other. We will make that more explicit in the next 15 minutes. Okay, because that, as you may think, but that leads already to a few caveats, because let's say we have our indices 3, 7, 3, 4, so now we have the index 3 here twice, and if we counted it as a NumPy array, this would be 0, 1, 2, 3, so this here would also have index 3. So what happens now if I want to get the third element? Well, it's those two, so it's this here and this here, but not this here. So it returns a series. This here is also a series, as we see, because it's formatted the same way. And if we have an explicit index, then the implicit index is not used. So when taking the array, the pandas series at a position and an explicit index, it's preferred in contrast to the implicit one. And like I said, the result of this is also series because we have more than one value. Yes?
So if you set an explicit index, does it need to have the same length, or what happens if you don't have the same?
It doesn't have the same length. This here, I don't even know what.
If you only have 3 elements with an explicit index.
Look, so it can't. You know about broadcasting, right? Rüdiger told you about broadcasting last week. So it can't broadcast this. So now we have values of length 4 and indexes of length 5.
Yeah.
It can't broadcast this. However, if we had a single value here, then it would be able to broadcast it. So it needs to match all the criteria for broadcasting. If you don't know what broadcasting is, we visited last week's lecture. So the criteria for broadcasting must be fulfilled. Yes?
So if you wanted to get the real third element, you would type something like 3 double dash, what's it called?
There's a method to get the real third element. We'll talk about that in
Okay,
a
cool.
few minutes. Okay, so this here is basically, so it's like a NumPy array which has another explicit index. But basically, you could also see it as a specialized dictionary because, well, what does a Python dictionary do? Well, in a Python dictionary, I can also get data at the position of the index B, right? So this analogy makes even more sense when we start defining our series using a dictionary. So this here is a normal Python dictionary, and then we make a series, and in the constructor we simply simply use this argument this dictionary, and this will make a series basing on this dictionary with the correct indices. Yeah.
So in the cell before that, we had data at position 3.
Yeah.
And could we now implicitly get data at the position 3 0 or 1, for example, because data at position 3 has 2 entries?
Oh yeah, I think you could just index that here again. Then you would have to say like this dot ilog, because ilog gets the implicit index, and then that would work. Yes. I will talk about what ilog is in a few minutes. Yeah, because the result of this is a series. You can index the series again. However, if you would index data 3 at 3 again, you would still get the same one because it still uses the explicit index, and still two numbers there. Okay, so this here looks like a dictionary, right? We could access this population at the position California, and we would get the population number for California. Okay. However, what we couldn't do with the dictionary is slice, and we can do that with a Pandas series. So we can say the population at the positions California until Illinois. And then we get the slice, which is, well, the third 3 elements. Note that normally when slicing, the last border, the higher border, is not included, whereas here in Pandas it's included. Because if we use explicit index, we include the upper bound. Okay. This I already showed you. If the data is a scalar and we have a number of indices, then it will simply project the data up until the number of indices, until it reaches the same number as the number of indices. So if I have a scalar and 3 indexes, I just copy the scalar 3 times. Yes?
What would happen if we had California twice in the...
That would simply work. I mean, you couldn't create it like this because you can't make a dictionary like this, but I could simply add another California here.
But how would the slicing be done then? So from the first occurrence of California to...
I think it's the first. Let's get to that later when I have a better example and when I can use log and ilog. Aaron?
Can we do the scalar thing the other way around too? So have one number for index only, multiple numbers for the other thing.
What do you mean?
The
I see.
index is only one thing.
Then you would have the same index everywhere. I don't see why that would make sense. No. You wouldn't want to do that anyway. I would turn it back. Okay, and data can be a dictionary. So we have here, well, it automatically orders the dictionary, right? I have here 2, 1, 3, but it automatically orders it if the data is if the index is a dictionary. And I can even make a series simply to a dictionary again by running the function, the method toDict, which make a normal Python dictionary of that. But note that if I have the same key twice in there, the dictionary will not contain it twice. Okay, so those are series. Series are 1D NumPy arrays. And now let's get to a data frame. And a data frame is simply a 2D NumPy array. So we can again see a data frame is a generalized NumPy array. So if a series is a one-dimensional array with flexible indices, a data frame is a two-dimensional array with both flexible row indexes and column names. So let's make a new dictionary, this area dict. So we had the population dictionary before. Now we also have an area dictionary, and we make a series out of that. So we now have a new series. Now we can make a data frame out of those two series we have. In fact, out of 3. Because, again, we can have a scalar here. Okay, so now we make a data frame. And in the data frame, we can have multiple, we have a dictionary of multiple series. So behind this key is this dictionary, behind this key is this dictionary, behind this key is the scalar USA. So now, if we print all the d-types of our new data frame, we see where the one column is an int, then the second one is an object, and the third one is an int again. Couldn't do that with NumPy, because NumPy would want to have the same d-type on all of that. And what it results in here is this. It's basically a table. It's a 2D, it's a 2D array, right? We have column names, and we have indexes for the rows. And this is basically a database. So everything, SQL databases, and basically all kinds of modern and actually used databases would look like this. So we have the columns. In the columns, there are values. There are different attributes, and in the rows, there are, so one row is one data point, for example. And the data point has certain values for these attributes. Okay, so we have the data point California, which has a certain area, is in a certain country, and has a certain population. And same for Florida, Illinois, and so on. Yes?
What if California was missing in one of the tables, dictionaries, and...
I will get there in a second. If it would be missing in one of the dictionaries, it would simply have a NaN there, because that would be a missing value. Pandas says missing values are not a number, and there I could print an NaN there. I will do that in a second anyway. Okay, so this here looks like a database. And this also looks like a generalized dictionary, right? I can get, for example, this data frame. So it's generally called df. If we have a variable, we always call it df for data frame. And this looks like a generalized dictionary, because I can access it at the position Illinois, for example, and then that would give me this entire row. Or I can get it at the position country, and it would give me this entire column. What of those does it do? We'll get there in a second. But yeah, the keys are names of the state, and the values are a list. Area, country, not country, population. Okay, and this being a generalized dictionary, where we can do some stuff with that. For example, we can sort it. The command for that is .sort_values, and then we have to say by which column we want to sort. Now we sort by population, so we start with the most populated state. And we could also, for example, access a certain cell of this, where let's get the maximum of this. And for this, we say we want the value which has in the column population the highest value. So this IDX_max is basically like argmax. This here states in the column population.idxmax returns the name of the row which is max in population, so California. And then we access this here by running states.log. And this here will then get the entire row of this. Oh, I used log already here, even though I didn't use it. Okay, and the data frame now has indices. So like the Python dictionary key, right? We have the index California, Florida, Illinois, and so on. It has columns, which is also an index. It's also an index object, area, country, population. And what it has values, and what its values is, again, a NumPy array, just two-dimensional. So basically what Pandas in this data frame does, it has underlyingly the index, the columns, and the values, and that's already it. So it's a generalization of a two-dimensional NumPy array. Okay, but again, we can see it as a specialized dictionary. Where we can access states at the position area. Note that if we're indexing a data frame with square brackets, we get the column. So this here gets the series, this here is a series, containing all values for this column with the respective key. Okay, so this here is a series always have keys, and where does it get the key? Well, from the index of the data frame. So what this results is a series of all the keys plus the corresponding value for the column area. Okay, how do we create data frame objects? Well, one way we showed already before, via multiple Python dictionaries, for example. You could also create it from a single series. So we can make a data frame with a population where we name the column population. So this is a rather useless data frame because this could just as well be a series, right? But it is now a data frame. We have a column, we have one column called population, we have the indices, California, Florida, and so on, and we have the values for the column. We can make it from a list of dictionaries, we showed that already before. And what Pascal, you asked, so if we now have, so this dictionary has a value for A and B, and this dictionary has a value for B and C, well, it makes normal rows out of both. So if we don't specify the name of the row, the key, then we simply start indexing 0, 1, 2, 3, and so on. And if we don't have a value for a certain column here, so it knows that the column C is in some of the data, but not in this one, so it simply say NaN, not a number, missing value. And here we have the A missing, so A is here, NaN, not a number, missing value. Yeah?
Why is the value of A 1.0 and the value of B 2.0?
Yeah, I wondered that too, actually. That didn't look.
Maybe because the not a number data type doesn't have the integer data type doesn't have another number.
That's fun. Oh yeah, because not a number is np.float64. Yeah, right. That's true. The NaN is actually a float, and because in this column there's at least one float, this here, it must make all numbers a float number anyway. Also, yeah, true. Okay. Yeah.
But can get in our way at some point, right?
What do you mean?
And I didn't think about it, but couldn't there be an example where you divide something and you assume that it's an integer, but because you have an NaN at some point in the
yeah, that's why the next lecture is all about missing values and how you deal with missing values.
okay.
So that's like 50% of what pandas is all about. You use pandas because pandas is good with missing values. Next week.
Except they're integers.
Apparently. Okay, yeah, we can make a data frame from a two-dimensional number array. So this here, date range, makes simply a series starting at this here's a date, the 1st January 2013. And this date range simply makes a series starting at this date, making, and in this case, 6 days. The lecture in 2 weeks is going to be all about, maybe, it's going to be all about time series, so you will see this probably a lot in 2 weeks. Just know that this here creates a series for now. Then we can call the constructor of data frame with a two-dimensional NumPy array. And we say now that the indexes are here the series of the dates, and the columns are, let's say, a list A, B, C, D. So this here is one way to make the indices, this is one way to make the columns, this is one to make the content, and the result would be this. As much for that. Any questions to creating data frames and so on?
Can you go back to the ABC example?
What is ABC? The one at the very top?
No, down. Next one.
Ah, this one.
How do we know what is the 0 and 1 as the row values?
It just makes them, if you don't explicitly say were values for that. So if I would, what is it here? I would say index, what was that? I would say index then we'll give this name. Just don't even know, I think it sorts them simply by order currently. Okay, data indexing in the collection. So we indexed by square brackets, we saw that already, but there are a few caveats, as we also saw already. So how do we do indexing? Well, we know from last week, from 2 weeks ago, can have normal indexing, slicing, masking, and fancy indexing. What are all of those again? So let's make a simple, I was just going to show you a few of them. This here is a simple two-dimensional NumPy array. Okay, and now normal indexing would simply, well, square brackets, one value. Slicing is square brackets, more than one value. So for example, separated by a colon. Masking takes a Boolean, an array of Booleans, and then yields the ones where this array is true. Fancy indexing simply requires a list of indexes. Okay, so for example here, this is a combination of fancy indexing and masking. So this here is A, and first of all we take A, we take the entire row, and the first and third column, yeah, and then we mask that, and we say the mask is where this is the same as this one, modulo 3 equals 0. So this takes from those two rows we still have, takes the one which are divisible by 3, which is 9, 3, 15. So this here takes those values of the second and fourth column that are divisible by 3. We can do the same thing in pandas. So again, it's nice to have those two analogies in mind of it either being a dictionary or a generalized NumPy array. So let's make, for example, let's make a new series, and we can check, for example, if B is in data. Like as if it was a dictionary, we look if B is a key, and because it indeed is, it returns true. And like a dictionary, we can have the .keys method, which is just like a dictionary, and it returns the same thing as the .index method. And like in a dictionary, we can call .items, which makes a two-dimensional list of key value pairs, which returns a two-dimensional list of key value pairs. And like in a dictionary, I can add a value simply by saying data at the position E equals 1.25. So like a dictionary. But we can also see series as one-dimensional array, because we can slice. Just that we don't have a number as index, but this explicit index. Data from A to C. If we use the explicit index, the upper bound is included, in contrast to Python. We can also slice by implicit integer index, but if we do that, the upper bound is excluded. So A, B are 0 and 1, and C would be the third, it's not in there. And just like in NumPy, I can do masking. So I can get data where the value for data is bigger than 0.3 and smaller than 0.8. Note, I always have to use, when masking, I always have to use the single AND and the single OR and the single NOT and the single XOR, because we want to have it bitwise, because we have a value for every single value of the array or series. So this here returns all values which are bigger than 0.3 and smaller than 0.8. Can do fancy indexing, where we provide a list of indexes, and that then returns a series, of course. And yeah. So what happens now if I make a series with indexes 1, 2, 3, 4, 1, 2, 3, 4, and then I slice it at the position 1, 2, 3? And now that's really confusing, because when slicing, I use the implicit. Wait, do I? This here is the implicit index, because this here is the first, this here is the second, and the third is included. So when slicing, I use the implicit index normally, and when taking one value, I use the explicit index normally. Isn't that annoying? Yes, it is. And that's why you shouldn't do that. So again, I can show you that again. So explicit when indexing. So here, this is on the series 1, 2, 3, ABC. So I index at 1, which is the explicit one here, not the B. And implicit when slicing, I take the second until the third one, including the fourth, right? Excluding this one. So I take those two ones. Isn't that annoying? Yes, it really is, and that's why you shouldn't use that, and that's why you always should use, please be explicit about what you do. There are two methods, and that is .lock and .ilock, and .lock always use the explicit index, so if I say data.lock at the position 1, it behaves like this here, takes the explicit one, but if I say data.lock at 1 until 3, it still uses explicit. Because this here has the explicit index 1, this here is the explicit index 3, I say data.lock 1 till 3, it will get both. Because the explicit when using explicit indexing, it always it includes the upper bound, we have two values. And ilock does the same, but for implicit index. So data.ilock at the first position takes the first one, so 0, 1, which is a B, and data.ilock from 1 till 3 takes a 0, first, second, third is excluded, so it takes those two values. Okay, so save yourself the pain and always be explicit about what you do. And why that? Because the Zen of Python says, as Rüdiger showed you last week, explicit is better than implicit. Because you're going to fuck something up. If you don't, then you don't know why. Okay, as much for serious data selection and data frames. So let's make this, we had this data frame already, we just removed the column here. And now if we index a data frame, I said already we index the column. So data at the position area gets the column of that, of the areas, which was this one here. And what it is a series. So it returns a series. Data at the position area is a series of all the keys and the values for area. We could also, instead of using square brackets, we could dereference, but that leads to side effects. Because if I would call data.pop, which is in fact a column, but it's also a method. Because pandas is an iterable, and iterables have the pop attribute. Like it is one of the iterables that has the pop attribute. So I just wouldn't dereference at all. I would always index using square brackets. Yeah, and the type, if we get a column, if we can get the values and the data values, we saw that already. And that is, again, so underlyingly, why did I just show that again? Underlyingly, it uses a numpy array. Yeah, because, why do we have that? Because, well, underlyingly it uses a numpy array, and with this picture in mind, we can think of all the numpy functions we know, and they probably also work on pandas. So, for example, we had the method to transpose, which we implemented even ourselves, right? So, transpose, a method which has a decorator property, if we transpose it, well, we simply swap the columns. We swap rows and columns, as we see here. So when transposing pandas keeps nice, thanks, luckily enough, it keeps the correct labels. Okay, and again, for array style indexing, we still use lock and ilock just like we do in series. Okay, ilock for the underlying numpy index and lock for the explicit index. So data, and then of course, because the data frame is two-dimensional, if we use lock and ilock, we can provide two values, right, for x and y. So this here gets data from the third on. So data is not this, but this is data that transpose, right? So this gets it until the third state and until the second column. Starting counting from 0, excluding the upper bound because it's ilock. Okay, and just like that, we could use lock, and lock is the explicit index, so we want rows until including the Illinois, and columns until including the population. So if we want to get, for example, an So I said that if we use, if we index it, we normally get the column. So if we want to get not the column but the row, we have to say data.log and then the name of the row and then a colon because we want to get the entire row. And well, if we want to get 2 columns, we can say data.log and then, for example, a colon and then the columns. So this here gets entire rows, columns. This here gets entire rows, obviously, just like in NumPy. Okay, and using this, so having the analogy still in mind, we can also use vectorized calculations to, for example, add a new column. Let's add the new column data density, so population density, which is data population divided by data area. So this here is obviously a ufunc. It's a vectorized function because it takes every single value of the column population, every single value of the column area, and well, divides every value of that by every value of that and makes a new column out of it, a new series. This results in a series, and then we assign the series to the column density. And then we add a new column to our data frame, density. And then if we want to get, so this here is how, for example, how we would get all the population and the population density of all states which have a density of bigger than 100. So we can combine masking and fancy indexing. We want data at the position where the population density is bigger than 100, and we want the columns population and density. And the ones which have a population density bigger than 100 are Florida and New York, of this small data frame. Yes?
Can you also perform simple like multiply it by 2 or something instead of?
Sure. Can do almost anything. I don't know what the use of this would be at this point, but yeah. Okay, yeah, well, indexing refers, so again, another caveat which is really annoying if you don't use log and ilog explicitly. Indexing refers to columns. So if we simply say square brackets in that area, we get a column, and slicing refers to rows. You have to just remember that, it's really annoying for that. Again, please be explicit about your indexing to save yourself from a lot of confusion. So this here, why doesn't that work? If you don't plot it, you don't see that it's actually empty and you wanted something completely else. Just be explicit about it and save yourself from a lot of confusion. Okay, if you only want a single member, you can use .add. It's a bit faster than using .log. So this here doesn't accept the slice, but only 2 explicit values, and that returns one data point, and this is a bit faster than using .log. But if you do it often, you will see the difference. Boolean indexing. This here we made already before, and now we add a new column, which is 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. And then we can use Boolean indexing. So, for example, we can use isIn. Note that we want to check for inness, we have to use isIn and can't use the normal in operator because it's not binary. Hint, hint, you may need that for the homework. And so what this here does, it gets all the values of this data frame where the column E is in the list 102. So this here gets all the columns of the data frame, all the rows of the data frame, where the column E is either 1 or 2. So this here, this here, this here, and this here. And then sets them to missing value. So the entire column is now missing value. And now we could check, for example, for missing values using isNA. Right? This gets a new data frame which has 2 false, so 2, 2, 2, true, false, false, right? And then we can check for if there's any in a row, using that any x is equals. And then, for example, we could get the ones which are not empty using df at the position where this here is a binary not, where it's not NA, so not a number, and get those where not any of those is actually not a number, which now, because we set 2/3 of this data frame to a number, returns on 3 rows. And df.drop_na does the same as those two here. It's this line. But next week, missing values and so on, really important topic. Rüdiger is going to talk about that far longer than I do right now. Okay, multiple indexes. So we only had series and data frames now, which are 1D and 2D. What about if we want to have something three-dimensional? So we want, as index, we don't want only the state, but also the year where we counted this population. What we could do, even though it doesn't make much sense, is we could have, well, a tuple here of indexes here, which this is possible, but not really accessible and not really good. Pandas does have data structures, panel for three-dimensional data and panel 4D for four-dimensional data, but they're not used, but instead we have hierarchical indexing or multi-indexing. So how do we make multiple indexing? Rüdiger is going to talk about that also, I think, so I'm not going to talk about that for too long. But we could, for example, get here, we use pandas.multi-index from tuples, and then we provide those tuples here, and then we re-index our series here such that it now has this multi-index. Now this here has a multi-index, which looks much nicer, because we can access population at California, which will then return those two rows, and we can index that again at the position at the index 2010. So we can use multiple indexing. It's a multi-index. Okay, and this here is basically an extra dimension. So just like, so you can imagine this here is the first dimension, and then the 2000 and the 2010 are basically in third dimension behind each other, right? So this is actually an extra dimension. And yes, this here is rather useless because we have a series which has two indexes, right? And we simply make it a data frame. And yes, that's actually useless, and Pandas has a simple method to make a normal data frame out of a 2D series, which is unstack. So unstack takes a data frame which has multiple indexes, which we see here. In fact, it does, and makes a normal series out of that because, well, two indexes, that's what a data frame is made for. It's two-dimensional. We can also say which level we want to unstack at. And if we say, so the standard is level equals 1, which will result in this, could also unstack at level equals 0, which we would yield in the transpose variant. And if we now stack that again, we would have our previous series, just that we swap the indexes. So this here dot unstack level 1 dot stack yields this here in the other direction with the indexes in the other direction. Makes sense? Makes sense. Okay. What else could we do? So this here is just that if you have a data set, yeah, and the indexes don't look the way you want them to look, which you have to play around a bit with unstacking them maybe or resetting the index, and this is why I'm just showing you these functions such that you have seen them before because they can be really annoying. So let's look at our two-dimensional series population again, and we can redefine the index names. So pop.index returns those two here, and we can now set the names, and because we have two indices here, we have to set two names, and now we gave it names. Now we have, the indexes simply have names. If you, for example, load a series from a CSV file or something, they will probably have names because the first row in the CSV file will be the names of the indexes. And yeah, so if we want to make that flat again, this is still our two-dimensional series. If we want to make it flat again, we can reset the index and say, well, oh no, that doesn't make it flat because that makes a data frame out of it. If we reset the index, it basically makes a data frame out of that, and then even we keep our names here in this case, and we name our column, the only column we have because the series is one-dimensional, we name that population. What else am I doing here? Okay, so now we have this here is our pop flat because it's a flat, not multi-indexed data frame, right? Population flat. And we can also set the index anew here because we wanted to have state and year being the index. This makes it flat. Oh yeah, this makes it flat because now we have a new key. Because we did reset the index fully, and we simply made the previous index, we resetted the index, and we made the rows. and we made a new index. But having simple numbers index is not what we wanted. So what we want to do here again is, well, let's set the index again, and let's say the index here is the column state and the column year. So this here now is a multi-index data frame. So you see, because they're bold, both are indexes, so we have to access population at state and year to get a value. And now this could have more than population only, right? We could get population and population density for California in the year 2000. And so this is why we would need a data frame here. Good, because this may look confusing again and may not look exactly the way we want it to be. We can also rename this axis here to none, because we have our axis, our index, is 2 items. We'd have to give a list for renaming the index here to, well, it's 2 times none. So now it looks basically almost the way we want to have it. And if we now unstack it again, we made out of this. So now we unstack not a series, but we unstack the data frame. So this here is a data frame with 2 dimensions, because this is the first index, this is the second index. So it's 2 indices. And if we unstack that, we make a flat normal data frame out of this again. Okay, I renamed the axis here again. Where did I? Oh, because this here I didn't save. And if we now, so this here makes a normal 2D data frame. Data frame is always 2D, which is only 1 index, and then makes normal columns out of this. I just have this here such that if you see something which doesn't look the way you want it to look, you can relook at those functions here and see how you make it the way you want it to look. So this is just for your reference here. Okay, let's look at our pop flat again, which I saved somewhere further up here. This is pop flat. Yeah.
So there are like 2 columns which are population columns now, like in the
Wait, where?
above. We have like the 2000 column and the 2000
Yeah.
column, which are both kind of population columns.
Yeah.
How do we deal with it? Is this column called 2000 now, or is it called population in 2000?
No, this entire thing is called population, and this column is called 2001. Oh wait, actually no, you're right. This is population. It's called. How would we access that now? Oops. Wait, was there a string index? First level is still population, so we have to access. You're right. So we have to access ISDF at the level at the first index population, and this here then is a normal one, and then we would have to get 2010, for example. Oh, why doesn't it work? Oh, that's an integer.
Okay, cool.
Yeah. So that was actually. So if you plot yourself.columns, you will see what the actual multiple indexes are. Yeah. Okay, as much for that. Looking at pop flat again. Well, what did I do here? Well, I set the index to states. Oh yeah, because now I set the index, so I used to have numbers here as indices. I didn't want that, so I say, hey, yo, this states here is now the index. And then I renamed this axis because I didn't want the state name to be here because it's an index. Okay, so now if I access popdf2 at California, I will get a series containing those 2000 with the population and 2010 with the population. So now this is, wait, what? Oh no. Always be, oh shit. Always be explicit about what you do. Always be explicit. Oh yeah, it's not a series, it's actually a data frame. Sure, it can't be a series because a series would be only one row, so it must be a data frame because it's 2 rows and therefore 2-dimensional. Yeah.
So now you, in rename X's, you use none.
Yeah.
Can you use none or NaN?
None just means the name is none. You can't use not. That's not a missing value. The name of the X's. It's a column description. So it's this here, and that's not a value. It's just none because I don't want any name at all. And because I was annoyed by the name. It would look worse if I had the name there. Yeah.
Jan had this question about when you have explicit slicing and you have multiple values, then how the slicing would work. So
Yeah, that's
from California to Texas, how does it look like?
Oh yeah, I wanted to get actually right here. So it always includes the entire thing, which does make sense because you want all values which include Texas. Now, yeah, it will always do, even if there was something in between here, it would get that too because it wants the entire Texas. Yeah. Anything else? Okay. Why do I reset the index here again? Oh yeah, because I was not happy that I had the status index and I wanted those stupid numbers again. Just playing around with it, just that if you need something, you can just look at it. Okay, then reading series and data frames. So we want to get, because we need that definitely for the homework, you want to get series and data frames from CSVs because normally you have data sets given as Excel files or as HDF5 files or as CSVs. So let's look at, we have here a file Pokemon.csv which contains Pokemon. So and what do we do now if we have a CSV? So we have a new data set. Somebody gave you this data set and you don't know what it is. You want to know what it is. So I'll do first, well, the command to read it is pandas.read_CSV with the file name. So, and now what do we do if we don't know anything about this? Well, let's look at it. So df.head looks at the first 5 rows of that. So we see, this has a number, it's a name, a type. This appears to be a string, this appears to be a string, this too. All the others are numbers. This here is a number, this here is a boolean. Okay. Next, what we want to do, for example, is so pandas has the method describe, which for numbers, which for columns which contain numbers, not strings, gives you, for example, so it gives you the count. So there are obviously 800 rows in there because all the columns here have 800 values. The mean, so the mean total stats for Pokemon is 435 for whoever was interested. The standard deviation, minimum value, the percentiles, and the maximum value. And this is the median, right? So now you know that the median HP value for a Pokemon is, for example, 65. Okay, this doesn't show strings. For strings, we could, for example, use value counts. So value count simply counts how many each value of that string was there. So we have 112 Pokemon which have type 1 water. We have only 4 Pokemon which have the first type fly. It's legendary from Black and White. I caught it. Anyway, yes. But now we have, as we see here, we have an index which we don't want because we didn't use. So in the data set we see that here the hash symbol stands for a number, but we don't have the numbers index. But pandas create a new index. We don't want that. If we don't want that, we simply say that we can specify an index column. In fact, read CSV and for that matter, read Excel and read HDF5 have a bunch of parameters. And if you want something like if you want to exclude rows, or if you want to get only until a certain number of rows or whatever, there's probably an argument for that. And just look at the docs of pandas. Okay. Why do I play around with that here again? Because I wanted the index to be exactly right. So this here now, we see that we have multiple Pokemons which have the same number, like Mega Evolves, or this, whatever this is, we play this generation, has the same index. And therefore, well, what about resetting the index? We see that there are 800 Pokemon in there, but the index only goes until 721. Well, what about removing duplicates? I want every Pokemon to be there exactly once. To do so, I use the method drop duplicates. Rüdiger is going to talk about that next week. So let's drop duplicates. And duplicates are defined only by the column number. We set the index of that again because we need to. And then drop the column. So this here drops a column. drop index x is 1, this drops the index column. And now we see, so the number here starts counting at 1 as we saw before, right? It starts counting as 1. Now we see if we remove the duplicates from number, we have as many, we have now 720 items, rows in there, and 721 rows and 721 Pokemon. So yeah, remove the duplicates. And let's just save that to a CSV again. But let's say this here is now the new index again, so this column. And the method to save to a CSV is .toCSV. Now in the files we have a new no duplicate thing where we, for example, lost the Charmeleon Mega Evolve and so on. Yeah?
Does it keep the first version of the duplicate? Because, or
it keeps, yeah. Drop duplicates keep the first. You can specify which one you want to keep. But if you don't have any arguments, it keeps the first one simply. Okay, and now if we look at that again, oh yeah, you can look at it here, where we removed the Charmeleon Mega Evolve, the Charizard Mega Evolve, for example. Okay. This here we called it no duplicates. If we want to get only the ones where generation is 1, we could index it at the, so this here is masking, right? This is a Boolean mask, which is true for every row where generation is 1, false for all others. And we get now all rows where generation is 1. So this here will return, obviously, the first 151 Pokemon. Okay, and we can, for example, make a dict from that. So this here just prints the dicts until the 8th column, because otherwise it would be very long. But if we simply gen 1 at the position name, at the column name, .toDict, it will make a dictionary out of the number and the name. Yeah. Okay, almost done, because I don't need to do the last parts because it's not necessary for your homework. ufuncs. We know already ufuncs, universal functions, that we can, for example, apply something to all values of a number array. It's basically the same with wonders. And aggregations is simply where we only get one value from multiple values. So we have a series and multiple values, and calling series.mean would be an aggregation, because we aggregate multiple values into one B. Okay, so let's make a new series. Let's say the numbers from 0 to 6 and the square of that. And we can simply call it .sum. It's an aggregation, and it will simply take the sum of all of those. Or .mean, .median, .mean, .max. Those are all aggregations which are there. And the same for data frames. So imagine we have the same data frame, but we don't have only squares, but we also have the number to the power of 3. If we call .mean, it will call the mean from the row, from the column normally. So it will for each column generate the mean. But I can also say which axis I want. So saying mean, argument 1, or with the keyword argument axis equals columns, will now take the mean for each column. So this is how you use ufuncs, and those are the ufuncs which are there. We can count the items, get the first, last, mean, median, and so on. So those are the aggregation functions. Ufuncs are basically universal, vectorized, Rüdiger called them vectorized functions, functions that do something on every single value. This here is simply a random state for a number. You don't need to know, it's not important, but this here simply creates a data frame with values ranging from 0 until 10 and shape 3, 4, and the column names are ABCD. So this will result in this data frame. And if we now call the ufunc np.axp, so e to the power of, it will, luckily, nice for us, keep the column names and the row names. So this results in a new data frame which has the same column names and row names as the one before. Even better, Pandas does index alignment. This is what somebody asked before, I think. Didn't Bhaskar? I think you asked it before. So somebody asked, what if I divide and I have one value is not present? So let's say we have an area in the population series. The area series, there's Alaska, California, and Texas, not New York. And in the population series, we have California, New York, and Texas without Alaska. And we say one divided by the other. Due to index alignment, it will know that here California has to be divided by California from here, and Texas from here is divided by Texas from here, and Alaska is not there in the population dictionary, so it says, well, a missing value, not a number, and New York is not there in the first dictionary, so missing value, not a number. Missing values, so Pandas is really, really explicit about your missing values, and if one missing value in the calculation manual is missing, it will just remove them. Okay, why is that possible? Because dunder methods. Because a Pandas data frame has the dunder method divide, and that one is called when saying divided by. We can also, if we want to be more explicit, we don't want not a number here, but we say where we want a field value, if a value is not present, we can use the explicit version of the dunder method and say area.divide or area.__diff__. And then we can give as a new argument, as another argument, the fill value, which results into obviously two different things because we're dividing. So here in Alaska we have the case of we have the area but we don't have the population, so it's something divided by 0. Actually that's not a number because dividing by 0 breaks the universe, but because Panda uses NaN already for missing values, it will say something divided by 0 is infinity. And in this case, in the New York case, we do have a population but no area. 0 divided by something that's properly defined, that's 0. Okay, so if you have infinities in Pandas, that's probably because divided by 0, because Pandas doesn't use NaN for dividing by 0. Okay. That was serious. Can you do the same? Pardon?
NumPy also uses int.
Oh, I didn't even know that.
That occurred to me yesterday.
Okay. Okay. Yeah. So let's say we have data frames here. So now we have a small data frame which has A and B, and a big data frame which has columns A, B, C. If we add A plus B, it will align the rows and the columns, and for everything which is not there, it will say not a number, because A didn't have values for column C or for row 2. Okay. And now this is the last thing which I do need to show you. Not even. Okay, so some U-functions like CumSum or exponent are predefined by Pandas, but others are not, but we have the method apply. Oops. Okay, so let's look at this data frame here again and say df.CumSum is there because this data frame has the method CumSum. Data frames have the method CumSum, accumulated sum. But just as well, we could, so CumSum just happens to be there as a method from a data frame. But just as well, we could use the normal np.CumSum and use the method apply. Apply takes a function and applies that to every single value. So those here are basically the same. We can say the data frame at the column B CumSum, so at the column A CumSum is this command, which puts this series here, or we can say it's apply the NumPy CumSum and make a new row out of that. So apply takes an arbitrary function. And using lambda functions, we can take our own functions, right? So what we see here, if we call apply, and in our function we simply have, we print whatever this input is, just to look at what the input is to our apply function. So, and the input is this series, then this series, then this series, then this series. So apply takes a function, and this function gets as only argument, the entire series corresponding to the row if we call apply on the data frame. Okay, so we can, for example, have the function, and then it sets this this row to whatever the value was. So in this case, we just print returns none. So the result of that is actually none for every single row. Knowing that, we can use in our apply, for example, stuff like taking the maximum of that series minus the minimum of the series, which normalizes value. So if we df.apply and then make a function which takes the minimum of that row, which takes the absolute difference of that row, the range of that row, that here yields in a series which contains the range of the row. Okay, apply works for both data frames and series. So this df at the column A returns a series, and we can apply that. We can apply to series 2. Let's look at what apply does by using a simple function that only prints. And if we use apply on a series, every single value is going to be the argument of a function. Okay, and because print doesn't return anything, the result of this is everywhere now. So what we can, for example, do is we can make a new column A normed, which basically, so this here is a series. Therefore, if we call apply, it will get every single value for every single row. And for every single value, we divide this value by the mean of the entire row, and we have no other way of getting the entire row by simply calling the mean on this row. And this here then normalizes the row A. So it divides every row by the mean of the row. It divides every element by the mean of the row. And we can even use dictionaries with the apply function. So let's imagine we have this dictionary here of Z moves, to stick with our Pokemon example from before. This here maps a type to a Z move. And then if we look at our dataset again, and we then apply, well, simply a lambda function, which takes for every element here. So this here will be grass, 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 and so on, fire, and so on. And we'll get from the dictionary, so it will get the dictionary at that position and make that the row, and that here results in a series. We make this series, we make the row Z move, and then we added the new column, then we added the new column Z move for every single Pokemon. Hint, hint, you may need that in the homework. Good, and then the really last thing, real quick, group by. So group by is actually a combination of splitting, applying, combining. So what group by does, it splits, then we apply something, and then it combines again. So imagine we have the data frame ABC, ABC with some values, and if we group by key, it will split into, well, the ones where the key is A, the ones where the key is B, the ones where the key is C. Then we can apply some function on that. So for example, we can sum this entire thing, which will result in, well, one value for each key. And then group by combines it again into a new, into a new data frame. Split, apply, combine. This is group by. 1 second. So let's make this here. So this here, let's look at this, how that actually looks. This here is our data frame. If we now df.group by key, the result is, that's unexpected. It's simply a group by object. We would expect that df.group by key is a list of 3 data frames, yeah, but it's not, but simply a data frame group by object. And the data frame group by object is simply a view on the original data frame. It's lazy execution such because it's more efficient. So, and as long as we don't call any aggregation function, so any apply here, it doesn't do anything yet. So this here is only a group by object, and only if we apply an actual function on that, for example, sum, then it's actually executed. So df.group by key splits it, making a view of those 3 subsets. Then we apply the sum function, which will result into these 3 data sets, and then those are automatically combined. This reset index is just to make it look nicer, because otherwise we would have the stupid data here. Now this is, and now this here is the group by with the sum as applied function. We could also, for example, group by key and then only select the column data, which would select only the column here and would yield in a series, and sum that, and that would yield in a series, apparently. Yeah, so group by basically, even though it's lazily executed, group by returns a single data frame for every single part. So if we iterate over group by key, and so that yields 2 things, the key and the actual group. So we can loop over this group by, and if we look at the keys, well, the keys are ABC, well, because the keys were ABC in our example, and we can even print the groups and do something with the groups by simply saying, getting the second argument of looping over group by. And while not every method is given in a group by object, like I said, a group by object is a certain object, every group by object has the same methods than the original data frame. So, for example, describe is not there in the group by object, but it's there in a normal data frame, and thus I can call it on every single one. And it then combines the one of all the ones before. Those few are not really important. Don't need them. Then that would be it. Thanks for your attention.